This is a screencast for section 8.3, example 1. We're going to look at how the relative rates of growth are related to each other in two different curves. Now, we've kind of been looking at this since the limit days in chapter 2, but now we're going to look at why what we learned in chapter 2 actually is the way it is. So first of all, let f and g be positive for x sufficiently large. So we're limiting ourselves to positive x values. Now, the function f is growing faster than g as x approaches infinity if the limit as x approaches infinity of f of x over g of x is infinity. So you already know that if the degree in the numerator is higher than the degree in the denominator, the function is going to approach positive infinity. Or equivalently, the limit as x approaches infinity of g of x over f of x equals 0. So in other words, the degree in the denominator this time would be higher than the degree in the numerator, so the limit as x approaches infinity would be 0. F of x would be growing faster, g of x would be growing slower. Now, if they're growing at the same rate, the degree in the numerator and the denominator are the same, and that simplifies to be a constant. So like, 3x squared over 5x squared would be 3/5. And that means they're growing the same rate as x approaches infinity. So here's a picture. You got y equals x that's growing at a constant rate. The book shows that y equals e to the x is used as a comparison to show that a function is growing quickly because e to the x grows extremely fast for large x values. You can see it's already almost vertical just at 2. But then over here we have the function y equals the natural log of x, which grows very, very slowly. So that's used as a comparison for showing slow rate of growth. Before we get started in example 1, a very simple basic comparison would be, let's look at y equals x versus y equals 2x. So you know that the limit as x approaches infinity of 2x over x, the degree in the numerator and denominator are the same, so we say, oh, that simplifies to be 2, so the limit is 2, and now we can say that therefore they grow at the same rate, and that's why we can find their limit to be a constant. They grow at the same rate. The degree in the numerator and denominator are the same. So example 1 says compare e to the x and x squared as x approaches infinity. Show that the function e to the x grows faster than x squared as x approaches infinity. So if we're going to show that the function e to the x grows faster, maybe I want to take the limit as x approaches infinity of e to the x in the numerator and then x squared in the denominator. Now, if e to the x is supposed to grow faster, which it says I'm supposed to show that, so it would, I want to get that limit to equal infinity. Right now, that limit is infinity over infinity, so we need to use L'Hopital's rule. So I'll take the limit as x approaches infinity of derivative of e to the x is e to the x, denominator 2x. I still have infinity over infinity. One more time, L'Hopital's e to the x over 2. Now I don't have infinity over infinity anymore. I have infinity over a constant over 2, which is in fact infinity. So therefore, y equals e to the x grows faster than y equals x squared, because when you put e to the x in the numerator and take the limit as x approaches infinity, you get infinity. Now the other way to show that would be to show that x squared grows slower. So what if we put x squared in the numerator and e to the x in the denominator? Well, you still get infinity over infinity. L'Hopital's will do 2x over e to the x, still infinity over infinity. Now we'll do 2 over e to the x, which is 2 over infinity, so that would be 0. The limit as x approaches infinity of 2 over e to the x is 0. So then I've shown that y equals x squared grows slower than y equals e to the x, so y to the e to the x grows faster than y equals x squared. You do not have to show both ways. Either way would be completely acceptable. Your statement must say, though, that the function e to the x grows faster, because that's what you're supposed to show. Then now try problem number 1. Says show that e to the x grows faster than the given function. So e to the x grows faster than the given function. So I'm going to put e to the x on top and the given function on the bottom. Right now I have infinity over infinity, so I'm going to use L'Hopital's e to the x over 3x squared minus 3. Still infinity over infinity. Take the derivative of the numerator, derivative of the denominator again. Still infinity over infinity. Are you tired of this yet? And then numerator e to the x Denominator 6 after using L'Hopital's for yet a 1/2 time. Finally, we get infinity over 6, which is then infinity. So now I can make the conclusion that y equals e to the x grows faster than y equals x cubed minus 3x plus 1.